Hi, this is Bill Punch with another video from Michigan State University on the practice of computing using Python, CSE 231. This is a two-part discussion on the topic of perfect numbers. This is the first part, and we'll discuss what a perfect number is and how we can use the factors of a number to determine whether it's perfect or not. Let's go ahead and get started. So the perfect numbers are a distinction of integers known to Greek mathematicians. The way that you can determine whether a number is perfect is to find all its integer factors, those numbers that divide without a remainder, into the integer, and add them up. If the sum of all the factors is exactly equal to the number itself, then the number is deemed to be perfect. If the sum is greater, then the number is an abundant number, and if the number is smaller, it's termed to be a deficient number. There are lovely articles on the perfect numbers. Here's an example from Wikipedia, and it's actually a fairly interesting topic. It's not known whether there are an infinite number of perfect numbers. They have something to do with Mersenne primes, which has to do with security. But here then, from this list is another list. Here are some of the perfect numbers. The number 6, for example, is a perfect number. The factors to 6 are 1, 2, and 3. The number itself is not included, and of course the sum of 1 and 2 and 3 is 6. The same is true then for 28, 496, 8128. Those were the numbers known to the Greek mathematicians, and then it took some time before they found the next two very large numbers. What we're going to do today is see what has to be done in order to figure out whether a number is perfect. And in this first part, we're going to talk about a way to determine the factors of a number so that we can use it subsequently to determine whether they're perfect. And we're going to do it in two steps. We're going to do version 1. Here's our approach. We want to take in a number and we want to return a list of all of its factors. The way we're going to start is to create a single list, and we're going to have as its value the quantity 1. And so the list 1 we'll start with the factors, and 1 is always a factor in any number, so we start with that. Then we're going to look through the values from 2 through the number minus 1 and ask the following question. Is any one of those numbers, which we'll call factors, divisible without remainder for the number that we're looking at? And if so, we would like to remember it. We're going to do that by appending the number to the end of a list, and then at the end we'll return the list of factors. So here we go. We take in a number, right? We make our factor list starting with the value 1 because 1 is a factor. From 2 up to but not including numbers, so num minus 1, we're going to use the remainder function. If the factor we're looking at goes into the number without remainder, then we're going to append that factor to the factor list. Pretty straightforward. We can apply that to this number, just a big number, 1, 2, 3, 4, 5, 6, 7, 8. We waited a moment for that to actually go through, and we get the answer. Those are all the integer factors of our number. As we get to bigger number, this is going to turn out to be kind of slow. So what is it we can do to make it go faster? And this is what we would like to do in version 2. So in version 2, we realize that, we only need to check as far as the square root if we record both factors. So imagine we're checking the number 28. And we're checking to see if 28 is evenly divisible by 2. It is. We want to remember 2, but we might as well also remember 14, the other factor that goes into it, because if we keep going up through all the numbers, then we'll basically have checked 14 twice. And so we're going to check to the square root, and we're going to remember both factors as they occur. How are we going to do that? Or the math package, I should say, we're going to import it. Same thing, take in a number. We're going to remember the limit. We're going to take the square root of the number using the math package, turn it into an integer, add 1 to it just in case we had to round up. Same factor list that we had before, starting at 1. The factors are now going to be from 2 up to the limit that we just determined. If it turns out, and this is just a different way of saying the same thing, if number remainder factor is equal to 0, the not of that, remember 0 would be false, the not of that would be true. We're going to append the factor, but we're also then going to append the number divided by the factor. So imagine that this was 2, this would create 14, and we would append both of those to the factor list to get the same answer. Let's define the v2 function. Let's apply it on a larger number. This is 10 larger than the previous one, and it's instantaneous. much, much faster than the other way.